one example's in the books. Let's take a look at another one. So it looks a little simpler on the surface because we've got a quadratic instead of a cubic polynomial, but we'll see it's okay. We got this. All right, so we want to find a definite integral of 5 minus x squared as we let x run from -1 to 2. Graph provided. Again, remember, definite integral equals area. So we're trying to measure the area underneath this thing over the range we've got drawn out. Okay, our process is going to be the same. The catch here is we're going to use a different number of rectangles to estimate our area this time. So we're going to use 5 of them instead of only 4. So we need to figure out how wide each of our little rectangles needs to be when we divvy up this horizontal axis down here. So 2 minus -1 over 5. 2 minus -1 is 3, 3/5. 0.6, we're good to go there. Now, I kind of wish I'd done 4 again because it's easier to cut this thing up. So bear with me for a moment as I try to work this out. 1, 2, 3, 4, 5. Okay. Not quite as neatly to scale, but I've got 5 divisions there. Again, you may find it easier if you kind of temporarily erase the vertical axis so you don't end up thinking 0 ends up working. So working that out, we have -0.4. Then we go to positive 0.2. Let's see, that should be 0.8 and 1.4. A little more dense this time, but yeah, so now we can draw in rectangles the same way using either right or left endpoints. I'm going to start with right. So okay, so my right endpoint here is 0.2, 0.8, 1.4, and then lastly, what's going on? 2. Okay, so again, the vertical axis kind of messes with this, but I like the example. You will notice in this instance, we're not going to have a clear over or under estimate necessarily. You can kind of gauge what's happening based on what's going on with the picture, but these 2 rectangles, this one's a clear overestimate, this one a little bit of an overestimate, it looks like. So it actually should be cutting a little bit under, but that's fine. And then these are underestimates as well. That's pretty straightforward. But as far as the process goes, it's going to flow like it did mechanically earlier. So we have x, and then we have our f of x. Okay? Okay. So our right endpoints here, we don't use -1 yet because that's not a right endpoint, it's a left. -0.4, 0.2, 0.8, 1.4, and 2. And using my calculator's handy-dandy table feature, or if you prefer, you can just manually shove those numbers into the function inside the definite integral. If you prefer, I got the following. 4.84, that should be a 4. It's always been a 4. I didn't write a 9. 4.96, 4.36, 3.04, and then 2, I don't need to go look back at any notes or anything I've done because 5 minus 2 squared is in point of fact 1. All right, we add those suckers up, and I got 18.2. Yeah. Your calculator doesn't do that part for you. You will actually kind of have to crunch out the arithmetic, but it's not bad. It's adding numbers. You can do this. So this time around, I've got enough room because I don't have massive numbers of decimals. I don't need to write the dot underneath here. I've got to multiply this thing by this common width. Remember, each of these guys is 0.6 units wide. So we have 0.6 times 18.2. And when I worked that out, I got 10.92 for my result. And we call that SR5 in this instance, because it's a right-hand sum with 5 rectangles. Okay? All right. I'm going to leave the left-hand sum as an exercise for you to work on, But I did want to take a look at another way you might do this. I mentioned we don't specifically have to use endpoints. It's just convenient to grab them. You could instead pick some other point. Again, technically, you could pick a different point in every one of these, but that feels really random. What I'm going to recommend we do instead is use the midpoints of each of these guys. So I'd have somewhere in between these two. So I've got something like this. It's hard to tell the difference on that one. Back here, midpoint of those two, and midpoint right there. So that's what our picture looks like if we use these midpoints of each of these intervals instead. Now, I have done you the favor of going ahead and working out what those midpoints are. You can do it easily enough. Just average the two endpoints. That's fine. And when we do that, we're going to get the following. So we have negative 0.7, negative 0.1, which, yeah, it's a sketch. Positive 0.5, 1.1, and 1.7. Okay. Now we feed each of these guys into our integrand, or, just change the numbers in our table entry. Potato. So we have 4.51, 4.99. Let's see, that one's going to be 4.75. Yep. This one is 3.79, and then 1.7. Got 2.11 when I did this. Hey, look, it even broke out at the same place. I add these guys together, and I get 20.15. Am I done? Of course not. I haven't done anything with this delta x thing yet. I need to multiply this thing by the width of each of these rectangles I created. So from there, I got 12.09. We normally call that S with a subscripted M, midpoint. Hopefully that stands for reason. We're still using 5, so we got that guy right there for our midpoint estimate. And again, it's not immediately clear if this is an over or under estimate. You see, each one of these, it feels like we're kind of doing both, right? We're over and underestimating on opposite sides based on the whole midpoint thing. So those are our three main approaches that we're going to see. As I said, it technically doesn't matter how you do it, so long as you make sure you're grabbing one point inside each of these intervals and using that to evaluate your function to determine a rectangle height. So we've got some estimates. Again, in a process that may feel hauntingly familiar, what if we wanted a better estimate? There's a few answers you could give to that. On the one hand, you might try using different shapes instead of rectangles, but rectangles are really easy to work with. So if we could keep those, that'd be nice. The other thing you might try to do is maybe if we use more rectangles, if we tried to use more but thinner rectangles, like I cut each of these guys in half or something like that, I feed in, more of those guys and I won't have quite as big a gap. I'm not, catching as much extra area here maybe, so it feels like that would sharpen up our estimate. Hopefully you get the idea at this stage. Maybe we do that again. We use even more rectangles, and then we try using even more, and even more, and even more. Yeah, this sounds like some kind of limiting process. We'll get there and we'll talk about the limit momentarily, but before that, we're dealing with a limit of a summation at this point, and it gets really tedious to write down one of these things. I mean, technically you could do it in this table format, but then you're going to have some Excel spreadsheet looking thing that's 3 pages long, and your calculator isn't really good at handling that. On the other hand, you could just try writing these things out next to each other, like 4.51 times 0.6 plus 4.99 times 0.6 plus 4.75 times 0.6. Yeah, long summations like that are kind of a pain, especially when there's a particular rhythm to the way you're going to write them. It turns out there's an easier way to denote summations like this, and that's what we'll talk about in the next video.